This is section 15.4 on the number of signals that might be present in an NMR spectrometer. So the number of signals is related directly to, one, how many protons are potentially present in the molecule, meaning that if there's only one proton or hydrogen present in the molecule, then there's probably only one signal. However, with increasing number of hydrogens, you could have the chance to where several of the hydrogens appear to be what is called chemically equivalent. And chemical equivalence is a special topic in NMR spectroscopy because some protons, by symmetry, they give rise to the same signals, the exact same signals in NMR spectrometer. And if you take a look at this screen from a figure in your book, you can see a type of chemical equivalence here, or an explanation of that. Whereas if you look at this middle carbon, the two protons here specifically that are attached to it, if you rotate this molecule around this middle carbon 180 degrees, you could not tell a difference between either of these protons. Because this molecule has a rotational axis, those protons are identical, and we consider those protons to be chemically equivalent. These two protons here are chemically equivalent, just as these three protons are, and those three protons on the other carbon as well. Now, chemical equivalence is very important, as we'll see as we go on. And two protons that are chemically equivalent are said to be homotopic. Now, other types of homotopic protons are shown here, and they have each of them a 180-degree rotational plane. One easy way to find out if two protons are homotopic or not is to do what's called a replacement test. You draw the molecule first, and then you draw the same molecule again, except this time, one of each proton is replaced by a deuterium atom. If that yields the same compound, meaning that you can turn this one over and make this one, then the two protons are said to be homotopic. But that's not always the case. Take, for instance, this molecule. This is ethanol, and we're looking at the alpha carbon of ethanol. If you take these two protons, they are not homotopic, because when you rotate around the alpha carbon 180 degrees, you can see that now we have a mirror image that is not superimposable. What's interesting is that while these two protons are chemically equivalent in an NMR spectrometer, they are called enantiotopic because if you replaced one of them with a deuterium, now you would have a chiral molecule. So because you can do that, you can make a replacement and find a chiral molecule. We call this an enantiotopic proton, meaning through replacement, you make two enantiomers. A really weird thing about NMR spectrometry is that if you have an enantiotopic proton, if the solvent is not chiral, you won't see any difference in the two signals, whether you replace one proton or the other. However, in a chiral solvent, you actually do see a difference in the enantiotopic signals because of the differing chiral environment means that the molecules have different electronic environments around them, which changes the placement of the NMR signal. The last thing that we're going to talk about is a topic called diastereotopic protons. And these arise because protons are not chemically equivalent. The figure in 15.7 in your book really is a good one to explain the difference between homotopic, enantiotopic, and diastereotopic protons. Typically, chemically equivalent protons are enantiotopic and homotopic, but non-chemically equivalent protons are either diastereotopic or just not related. So an example of diastereotopic protons is shown here in your book with this 2-butanol. The protons on the third carbon of T-butanol are said to be diastereotopic. And you can see that illustrated closely thereafter, because if you replace either of the protons on the third carbon by a deuterium, then these are now mirror images, and so they are not the same molecule, they are not chemically equivalent, and you will see two different signals for each proton here. Slightly different signals, but they will be different. And one reason why they will be different is because this proton will experience a different electronic environment due to the close proximity of this oxygen. And that is section 15.4.